Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is ladder logic documentation. Our objective is to learn how to properly document a ladder logic diagram. We'll learn to comment functional blocks, number rungs, number wires, number terminals, identify devices and associated contacts, and perform numerical cross-referencing for logical elements in mechanically interlocked devices. Additionally, we'll discuss proper grounding and circuit protection practices. This lecture operates under the assumption you have watched the basic ladder logic lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Recall that ladder logic diagrams make electrical connection and function easily readable and apparent to those practiced in their use. As the ladder logic diagrams we examine increase in complexity, it is often necessary to provide guidance to their interpretation. Documentation allows a reader to reference specific rungs, wires, terminals, devices, and functional blocks, as well as see how related rungs affect each other. Not all the skills demonstrated in this lecture are universal in nature, especially wire numbering, and for this reason, I go to the trouble of presenting alternative techniques. If your employer uses a different technique entirely, I'm urging you to learn and use that technique to the exclusion of all others. This being said, the documentation skills and techniques as presented in this lecture are ordinarily commonplace. First and foremost, a ladder logic diagram is only useful if it can be properly interpreted. It is for this reason computer programmers comment their programs. Designers can hand off the diagram to a technician, and the technician can take it from there. Additionally, if a system must be redesigned, the comments and documentation remind the designer of the intended purpose. Ladder logic documentation can be as simple as annotating the description of a particular functional block on the right-hand side to whatever degree of detail necessitated. Note that I've identified the top group of rungs as those that control the hydraulic actuator. The middle group of rungs control the motor-driven pump, and the bottom group of rungs perform protection and diagnostic services. The purpose of particular functional blocks with easy-to-interpret descriptions makes this ladder logic diagram ever so slightly more understandable. Beyond this simple functional division, this ladder logic diagram may seem to be an incomprehensible soup of rungs, devices, and wires to those unpracticed in their use. Keep in mind, the title of this lecture is Ladder Logic Documentation, and I am not asking you to interpret this particular ladder logic diagram. All we're going to do is to learn how to properly document it. Later lectures on pumping circuits will make use of a derivation of this particular diagram and discuss it in great detail. For starters, we need to number the rungs. Let's start fresh and remove the functional block descriptions. Rung numbering is easy. Each rung is given a number starting at the top and working our way to the bottom. Rung numbers appear on the left. Rungs are defined as complete paths from the left to the right. Note that the holding contacts CR1A and P1 are both their own individual rungs. This particular ladder logic diagram has 8 rungs. Rungs 1 through 3 serve to control the hydraulic actuator. Rungs 4 to 5 control the motor-driven pump. Rungs 6 through 8 serve diagnostic and protection purposes. Rung numbering allows a technician to reference a specific conductive path from left to right. Now we need to number the wires. This is where things get interesting, because there are a lot of different methods of doing so, 2 of which I'll show here. First, don't think of them as wires, but rather nodes. Recall that a node is a common point of connection. Note that the right terminal of the e-stop is connected to a bunch of other devices. This is a common point of connection, and all devices hooked to this single pool should have the same voltage with reference to another point. That's really the purpose of wire numbering. Let's start with a fresh slate. Method 1. Method 1 starts with wire number 1 being the left upright. Everything attached to the left upright is given wire number 1. Notice I'm circling the wire number. There's really only one device attached to the left upright, the left terminal of the e-stop. Method 1 then has us skip the contents of the first rung and jumps to the right upright. all devices attached to this common connection are assigned the wire number 2. Note a number of different devices all have wire number 2 leading from them. I must again emphasize that wire numbering is better thought of as node numbering. A voltmeter from wire 1 to the terminal of any device hooked to wire number 2 should read the full pilot voltage. Now, method 1 has us return to our earlier point of departure and then assign numerically sequential wires from here. Everything connected to the right terminal of the E-stop is assigned wire number 2. This is a common point of connection. Now, method 1 has us move left to right and then top to bottom, filling in all the wire numbers as we go. Note holding contact CR1A in rung 2 has wire numbers 4 and 5 leading to it, since it is a common point of connection to wires sequentially assigned left to right, top to bottom in the rung above it. Similarly, note that holding contact P1 in rung 5 has wire numbers 7 and 8 leading to it, since it is also a common point of connection to wires sequentially assigned left to right, top to bottom in the rung above it. All in all, it looks like we top out at wire number 14 for this particular ladder logic diagram. Note this is 14 wire numbers, not 14 wires. As I previously stated, wire numbering is better thought of as node numbering. A lot of wires lead from node 2 and 3. However, they're all connected to the same place. Method 2. Let's start with a fresh slate. Before we move on to numerical cross-referencing and terminal numbers, let me briefly introduce an alternate method of wire numbering you may run across just to confuse the heck out of you. This isn't my favorite method because method 1 clearly identifies two very important wires, 1 and 2, as the left and right vertical uprights. Method 2 is a little sloppy in that there is no predicting what wire number the right vertical upright receives. This being said, a lot of manufacturers use this scheme, and it's something you should be aware of. Method 2 starts similar to method 1. First, start with wire number 1 being the left upright. Everything attached to the left upright is given wire number 1. Again, there is really only one device attached to the left upright, the left terminal of the E-stop. Method 2, however, does not skip the contents of the first rung and continues assigning wire numbers left to right until it reaches the right vertical upright. Once the right vertical upright is reached, all devices attached to this common connection are assigned this number. In this case, the wire number is 5. Method 2 then continues as did method 1, assigning wire numbers left to right, top to bottom. Notice we still top out at 14 wire numbers, only wire 5 is now the right vertical upright instead of wire number 2. I know, this method drives me crazy too. There's no way of predicting which wire number the right up rail receives in advance. It all depends on how many devices are in the first rung. For this reason, I prefer method 1. The left upright rail is wire number 1, the right upright rail is wire number 2. Wire numbers are then assigned left to right, top to bottom. This is the method I ordinarily prefer, and the method you'll see me use during the course of this lecture series. Before we continue documenting this ladder logic diagram, we need to perform a brief review on terminal numbering. Recall that control relays and contactors are characterized by a coil and associated contacts that switch their activated state when the magnetically linked coil is energized by pilot voltage. An 11-pin ice cube relay is ordinarily characterized by the coil from terminals A1 to A2 and 3 single-pole double-throw transfer switches where the first digit identifies the particular switch and the second digit identifies its deactivated state. A second digit of 1 indicates that it is the common servicing both sides of the transfer switch. A second digit of 2 indicates that it is the normally closed side of the transfer switch. A second digit of 4 indicates that it is the normally open side of the transfer switch. When the coil of this relay is energized, the normally closed side opens and the normally open side closes. Alternatively, a mini contactor control relay may feature electrically isolated single-pole, single-throw switches like this one. These control relays are ordinarily characterized by a coil, also from terminals A1 to A2, and 4 single-pole, single-throw switches, where the first digit identifies the particular switch, and the second digit identifies the switch's deactivated state. A second-digit pairing of 1, 2 indicates it is a normally closed switch. A second-digit pairing of 3, 4 indicates it is a normally open switch. When the coil of the relay is energized, the normally closed switch is open and the normally open switch is closed. Similarly, a contactor is characterized by a set of primary contacts that close when the magnetically linked coil is energized by pilot voltage. When the coil from terminal A1 to A2 is energized by pilot voltage, the primary L2T contacts would close. The L2T primary contacts are not included in the ladder logic diagram, but rather the primary schematic. Contactors sometimes feature an auxiliary pilot contact from terminals 1,3 to 1,4 that changes to its opposite state when the coil is energized. If the application necessitates additional functionality, an auxiliary contact block can be utilized that includes other auxiliary pilot level contacts. When the coil is energized by pilot voltage, these auxiliary contacts would also change to their opposite state. Note that the first digit in the terminal numbers for a contactor pilot contacts identify a particular switch, and the second digit pairing indicates that particular switch's deactivated state. A 1, 2 switch is normally closed. A 3, 4 switch is normally open. In keeping with this theme, limit switches, push buttons, and other switches ordinarily number terminals such that the normally closed side is terminals 1, 2, and the normally open side is terminals 3, 4. To properly document this ladder logic diagram, we need to include terminal numbers for each device. However, since relays and contactors have coils and associated contacts that can appear in different areas of the ladder logic diagram, we need to identify which contact and which coil belongs to which device by naming each device an associated contact. Alternate methods exist, limited only by your creativity, but my chosen method is this. Ordinarily, I identify the coil first with some recognizable name or letter, then assign each associated contact a numerically or alphabetically sequential identifier after it. Note the coil of this control relay is named CR1. It has two associated contacts put to use in this ladder logic diagram: the normally open contact CR1A in rung 2, and the normally open contact CR1B in rung 3. When the coil of CR1 is energized, both CR1A and CR1B would close. Beyond naming and numbering associated contacts, you'll often see me go to the trouble of using different colored pens. If you have this option available, use it. This isn't a common practice, but it is immeasurably helpful for interpretation. I can clearly see that when the coil of CR1 is energized or de-energized, it will affect the state of both CR1A and CR1B. Now that we've identified a device, we can number the terminals of control relay CR1 and its associated contacts. The coil terminals are A1 and A2. Let's assume this is an ice cube relay characterized by single pole, double throw transfer contacts. Since CR1A is the first switch associated with control relay CR1, the first digit is 1 for both sides. The leftmost terminal is the common, so its terminal number is 1, 1. The rightmost terminal is the normally open side, so its terminal number is 1, 4. Since CR1B is the second switch associated with control relay CR1, the first digit is 2 for both sides. The leftmost terminal is the common, so its terminal number is 2, 1. The rightmost terminal is the normally open side, so its terminal number is 2, 4. Let's see if we can identify the remaining devices and associated contacts using similar techniques. Note the coil of this contactor is named P. It has one associated pilot contact put to use in the ladder logic diagram, the normally open P1 contact in rung 5. The primary L2T contacts do not appear in the ladder logic diagram, but rather the primary schematic. When the coil of the P contactor is energized, both the auxiliary contact P1 and the primary contacts would close. Now that we've properly identified a device, we can number the terminals of the P contactor and its associated contacts. The coil terminals are A1 and A2. Since P1 is the first auxiliary contact associated with a P contactor, the first digit is 1 for both sides. Since this is a normally open contact, the second digits are 3, 4. Therefore, the terminal numbers are 1, 3, 1, 4. The primary contacts are given their proper L to T numbering. Note the coil of this control relay is named PR, short for pressure relay, since it's part of the diagnostic and protection services monitoring pressure. It has two associated contacts put to use in this ladder logic diagram. The normally closed contact, PR1, in rung 4, and the normally open contact, PR2, in rung 7. When the coil of control relay PR1 is energized, PR1 would open and PR2 would close. Now that we've properly identified yet another device, we can number the terminals of control relay PR and its associated contacts. The coil terminals are A1 and A2. Let's again assume that this is an ice cube relay characterized by single-pole, double-throw transfer contacts. Since PR1 is the first switch associated with control relay PR, the first digit is 1 for both sides. The leftmost terminal is the common, so its terminal number is 1, 1. The rightmost terminal is the normally closed side, so its terminal number is 1, 2. Since PR2 is the second switch associated with control relay PR, the first digit is 2 for both sides. The leftmost terminal is the common, so its terminal number is 2, 1. The rightmost terminal is the normally open side, so its terminal number is 2, 4. The terminals of all the logically interconnected coils and associated contacts have been numbered. The solenoid and pilot lamps will use whatever terminal numbers specified by the manufacturer. Let's just say they're 1, 2. Be aware that DC pilot-operated devices may be polarity dependent. If so, a manufacturer will indicate what is the intended high and low side. Overload contacts have their own unusual means of numbering. Ordinarily, normally closed overload contacts are identified by the terminal numbers 95, 96. And normally open overload contacts are identified by terminal numbers 97 and 98. Since the OLP contact is normally closed, this would be assigned terminal numbers 95, 96. Now, let's finish up by numbering the terminals of all the push buttons and automatic switches. All the normally closed buttons are assigned terminal numbers 1 to 2. All the normally open buttons are assigned terminals 3 to 4. The normally open pressure switch is assigned terminals 3 to 4. Finally, recall that switches being held in their activated state can be identified using one of two conventions, the gravity convention and the arrow convention. I prefer the arrow convention since it is immediately recognizable. The observant among you will have noticed that the mechanically interlocked float switch is not in its deactivated state, but rather being activated using the gravity convention. Ordinarily, gravity would be pulling the top switch open and the bottom switch closed. This may have escaped your notice, and for this reason, I highly recommend the arrow modifier. Note only one arrow is necessary since this is the same float switch with two electrically separate yet mechanically interlocked sides. The normally open side of the float switch, being held closed, is assigned terminal numbers 3 to 4. The normally closed side of the float switch, being held open, is assigned terminal numbers 1 to 2. All terminals have been properly numbered for this ladder logic diagram. Let's freshen up our ladder logic diagram and now discuss numerical cross-referencing. Notice how we've had to be very diligent about matching coils and associated contacts, even going to the trouble of color-coding them. There's a lot of inefficient back and forth, and essentially useless for colorblind people and black and white ladder logic diagrams. Numerical cross-referencing solves this problem by identifying which rung number the associated contacts appear on the right-hand side of the coil rung. For example, the coil of control relay CR1 in rung 1 affects the state of CR1A in rung 2 and CR1B in rung 3. Numerical cross-referencing for coils and associated contacts appear in parentheses on the right-hand side. Note the numerically cross-referenced rung 1 has 2, 3 on the right, meaning that when rung 1 is energized, contacts in rung 2 and rung 3 close. Note that rungs 2 and 3 are not numerically cross-referenced. The state of these contacts is controlled by something in rung 1, and they are not actively determining their own fates. They're just passive elements responding to conditions in rung 1. Similarly, the P contactor coil in rung 4 affects the state of the P1 auxiliary contact in rung 5. Rung 4 is numerically cross-referenced to include a 5 in parentheses on the right-hand side, indicating that when rung 4 is energized, something in rung 5 closes. Finally, the coil of the pressure control relay, PR, in rung 6 affects the state of the normally closed contact PR1 in rung 4 and the normally open contact PR2 in rung 7. Note that the numerically cross-referenced rung 6 has overbar 4, 7 on the right-hand side in parentheses. Note the overbarred 4. Overbarred rung numbers indicates this is a normally closed contact and will open when this particular rung is energized. Instead of an overbar, you might also see this written as an underline. Similarly, underline rung numbers indicates that this is a normally closed contact and will open when that particular rung is energized. Regular non-underlined rung numbers indicates that this is a normally open contact and will close when this particular rung is energized. This particular numerical cross-reference indicates that when rung 6 is energized, a contact in rung 4 opens and a contact in rung 7 closes. Again, note that rungs 4 and 7 aren't numerically cross-referenced. The state of these contacts is controlled by something in rung 6, and they aren't actively determining their own fates. They're just passive elements responding to conditions in rung 6. Finally, mechanically interlocked switches are normally numerically cross-referenced, albeit in a slightly different manner. Note the ugly dashed mechanical interlock. Not only is this aesthetically unappealing, it's confusing, especially if this mechanically interlocked pair of switches was to be used over a long span of rungs. It is for this reason numerically cross-referenced mechanically interlocked switches ditch the dashed mechanical interlock and use something I like to call house notation. The top switch receives an upside-down house pointing down to the rung it is mechanically interlocked with, in this case, rung 8. The bottom switch receives a right-side-up house pointing up to the rung it is mechanically interlocked with, in this case, rung 4. If you got 2 or more numerically cross-referenced mechanically interlocked switches in the same rung, referencing other numerically cross-referenced mechanically interlocked switches also in the same rung, my advice is to color or fill in the roof of the house with something identifiable. White roof mechanically interlocked with white roof, black roof mechanically interlocked with black roof, and so on. Using numerical cross-referencing for mechanically interlocked switches, we can see that when the normally open float switch being held closed in rung 4 is opened, something in rung 8 would close. Similarly, we can see that when the normally closed float switch being held open in rung 8 is closed, something in rung 4 would open, all without the necessity of resorting to an ugly rung-spanning dashed mechanical interlock. That's it. We have properly documented this ladder logic diagram. We described the general purpose of the functional blocks on the right-hand side. We numbered the rungs on the left-hand side. We numbered the wires. We identified devices and their associated contacts, and then numbered their terminals. Finally, we numerically cross-referenced logical elements and mechanically interlocked devices. The end state of our diagram should look something like this, leaving no doubt as to where you are and what you're doing. I'll zoom in on each of the 3 functional blocks so you can check your work. Here's the hydraulic actuator block, consisting of rungs 1 through 3. Here's the motor-driven pump block, consisting of rungs 4 through 5. Finally, here's the diagnostic and protection block, consisting of rungs 6, 7, and 8. Before we move on to illustrated example problems, let's discuss grounding and circuit protection practices. Recall that pilot voltage is ordinarily provided by a step-down transformer in the case of AC pilot voltage, or a DC power supply in the case of DC pilot voltage. Circuit protection devices like fuses can be incorporated in the high, low, or both sides of the control transformer, or the input or output of the DC power supply. Systems using ungrounded pilot voltage are sometimes referred to as floating, and that there is still a voltage differential between the left and right vertical upright, but since it's not referenced to ground, any voltage measurement employing ground as a reference is essentially meaningless. Any voltage measurement on pilot devices must therefore use 2 points with some electrical reference internal to the floating system. If, however, pilot voltage is to be grounded, it is customarily done so on the right-hand vertical upright. Now, any ground connection can be used as reference for a voltage measurement. Grounding one side of the ladder logic diagram serves other purposes, as we'll soon see. Grounding the right-hand side of the ladder logic diagram reinforces one of the earlier rules we discussed in the basic ladder logic lecture. Switches on the left, outputs on the right. This is to suggest that ladder logic always uses high side switching arrangements, and that the closure of a series path from the high left rail to the low grounded right rail energizes the output device in each rung. This is sometimes called sourcing, and that the closure of the switch connects the grounded output device to the source. This is in contrast to a low side switching arrangement with outputs on the left and switches on the right. This is sometimes called sinking, and that the closure of the switch connects the output device at system voltage to a path to ground. Safety considerations dictate the preference of high side over low side switching arrangements. Consider an errant connection to ground in the high side switching arrangement. In this case, coil A couldn't care less about this errant connection since its A2 terminal is already at ground via the grounded upright vertical rail. The A coil remains de-energized. Now consider the same errant connection to ground in a low side switching arrangement. In this case, the A coil has a path to ground in parallel to the open switch. Coil A energizes despite the switch being open. Low side switching allows an errant path to ground to unexpectedly cause a fluid power actuator to move or to start a motor. This is to be avoided, and the reason why high side switching arrangements with switches on the left and outputs on the right are preferred. The one exception to this rule is the overload contacts associated with motor starters. Grounding the right-hand side additionally serves to ensure the proper operation of circuit protection elements. Consider a DC power supply with fused output providing pilot voltage to a high side switching arrangement. Consider the repercussions if an errant connection to ground was made not at the A2 terminal, but rather the A1 terminal. With a switch in the open state, coil A would still remain de-energized. If, however, an operator closed the switch, the errant path to ground in parallel to coil A would provide no opposition to current flow, and current would spike to great magnitudes. The circuit protection device on the high supply side would, however, detect this event and open as intended. Alright, that's it for new content. The remainder of this lecture will feature 3 ladder logic diagrams left as exercises for you to properly document. Here's example problem 1. I've already included a brief functional description on the right-hand side and properly identified devices and their associated contacts. Note the right-hand side upright rail is grounded. The ladder logic diagram uses high side switching, and the DC power supply has a fuse on the supply side. I've already numbered the terminals of the buzzer and the pilot lamp. I leave it to you to number the rungs, number the wires, and number the terminals of all devices, and numerically cross-reference logical elements and mechanically interlock switches. Again, don't worry about what this ladder logic diagram does. Just document it. By all means, pause the lecture and give it your best shot. If you number the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note that I'm using my preferred technique where the right-hand vertical upright is wire number 2. If you number the terminals for CR1 correctly, it should look like this. Note the coil terminals are A1, A2, and we're assuming that this is an ice cube relay with single pole double throw transfer switches. CR1A is the first contact, and it is normally open in nature. The left side is terminal 1-1, the right side is terminal 1-4. CR1B is the second associated contact. Since it is normally closed in nature, its terminals are 2-1, 2-2. Note that the float switch is a normally closed switch being held open via the gravity convention. As such, the terminal numbers would be 1-2 and not 3-4 for an ordinarily normally open switch. If you didn't clue in on the gravity convention, the comment on the right-hand side should have been sufficient. I'd like to say I did this as a teaching moment. However, I really just wanted to see you walk into a tiger trap and watch you die a slow, horrible death. Remember, the gravity convention dictates the switch's deactivated state. The schematic is drawn such that gravity would ordinarily pull the switch closed. However, it's being actuated into its activated open state by being immersed in liquid. It's for this reason that I ordinarily use the arrow convention that makes it explicit and obvious the normally closed float switch is being actuated into its activated open state. Don't walk into this tiger trap again. I guess I did teach you something in a twisted, devious sort of manner. If you numerically cross-reference the logical elements in mechanically interlocked switches, your ladder logic diagram should look something like this. Rung 1 has 2, underline 4. Note the underline 4. This means something closes in rung 2 and something opens in rung 4 when rung 1 is energized. Here's example problem 2. I've already included a brief functional description on the right-hand side and properly identified devices and their associated contacts. Note the right-hand side upright rail is not grounded, meaning pilot voltage is floating. Still, the ladder logic uses high side switching, and the control transformer features fuses on both legs of the primary. The one exception to the high side switching rule being the normally closed overload contact, which I've already numbered the terminals 95, 96. I've also already numbered the terminals of the primary contactor and overload relay. I leave it to you to number the remaining rungs, wires, and terminals of all devices and numerically cross-reference logical elements and mechanically interlocked switches. By all means, pause the lecture and give it your best shot. If you numbered the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note I'm using my preferred technique where the right-hand vertical upright is wire number 2. If you numerically cross-reference the logical elements, your ladder logic diagram should look like this. Note that when rung 1 is energized, something in rung 2 closes. The normally closed manual buttons would receive terminals 1, 2. The normally open push buttons would receive terminal numbers 3, 4. The auxiliary M1 contact, being normally open in nature, would receive terminals 1, 3, 1, 4, and the M coil would have terminals A1, A2. Finally, if you're up for it, here's example problem 3. Note I did not include a brief functional description on the right-hand side because I don't want to confuse the heck out of you. However, I did properly identify devices and their associated contacts. Note I'm not using a color scheme for this particular example problem. I leave it to you to number the rungs, wires, and terminals of all devices and numerically cross-reference logical elements in mechanically interlocked switches. Let's assume all the control relays are 11-pin ice cube relays with single-pole double-throw transfer contacts. By all means, pause the lecture and give it your best shot. Good luck. You'll need it. If you numbered the rungs correctly, your ladder logic diagram should look like this. If you numbered the wires correctly, your ladder logic diagram should look like this. Note that I'm again using my preferred technique where the right-hand vertical upright is wire number 2. If you numbered the terminals correctly for control relay CR1, your ladder logic diagram should look like this. If you numbered the terminals for control relay CR2 correctly, your ladder logic diagram should look like this. Since we're currently discussing these logical elements, we might as well go ahead and numerically cross-reference these also. The numerically cross-reference rung 1 indicates that when rung 1 is energized, something in rung 2 closes, as does something in rung 4. The numerically cross-referenced rung 4 indicates that when rung 4 is energized, something in rung 3 opens. Note the underlined 3. The normally open manual start push button would get terminal numbers 3, 4, as would the normally open pressure switch 1 and the normally open limit switch 1. The normally closed proximity switch PX1 would get terminal numbers 1, 2. Note that the mechanically interlocked limit switch 2 is being actuated into its activated condition. This can be made explicitly clear using the arrow convention. Similarly, note that the normally closed proximity switch PX2 is being actuated into its activated open condition. An arrow convention makes this explicitly clear. The normally closed terminals of the limit switch 2 being held open would therefore get terminals 1, 2, and the normally open terminals being held closed would get terminals 3, 4. Similarly, the normally closed terminals of PX2 being held open would receive terminal numbers 1, 2. If proximity switch 1 and 2 were part of a 3-terminal single-pole double-throw transfer switch device, you might see these terminals called 1, 1, 1, 2, where the 1, 1 terminal is the common and the 1, 2 the normally closed side. Let's assume all solenoids have terminal numbers 1, 2, where terminal 1 respects the required polarity of this DC pilot voltage. Finally, let's ditch the ugly dashed mechanical interlock and numerically reference the mechanically interlocked limit switch 2. Note the normally open side being held closed in rung 1. When this reopens, something in rung 3 recloses. Note the normally closed side being held open in rung 3 indicates something in rung 1 reopens when this side recloses. Alright, this about wraps up our introduction to ladder logic documentation. These skills might seem confusing at first glance. However, there really is a system behind it, and it simply takes repetitive exposure to the system to figure it out. A properly documented ladder logic diagram leaves no doubt as to what particular function, rung, wire, terminal, and device a technician is referencing and how it influences other rungs, logically or mechanically. If you require more practice in this skill, you will be afforded ample opportunities to do so in later lectures. This lecture series would be prohibitively long if I documented every single ladder logic diagram, and most of the following lectures use undocumented diagrams as opportunities for you to put this skill to use. In conclusion, this lecture introduced ladder logic documentation. We discussed annotating the description of functional blocks, rung numbering, 2 different methods of wire numbering, terminal numbering, device and associated contact identification, and numerical cross-referencing logical and mechanically interlocked elements. Finally, we discussed grounding and circuit protection practices. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.